later we have discussed about when it will be like kind of class 1 mechanism, class 2 mechanism, when it will be rocker mechanism, when it will be crank rocker or crank mechanism, all those things we have discussed. And today we'll go through, you can say, one problem, okay, where you'll just see how to use that particular grasshopper so as to check what kind of it is particular mechanism that is given that falls under which type of, you can say, category of mechanism, whether it's a class 1 or class 2. And after that, from there, using that particular logic, okay, which link is fixed, etc., then you'll be able to find out what kind of inversion of your graph of linkage that particular type is. Okay, so let's consider this simple configuration. So you have to indicate the class and type of each of the four mechanism that is shown here in this particular figure. So there are four mechanisms that is shown here: A, B, C, and D. And the link lengths are actually given. And what you have to do, whether it falls under class 1 mechanism or class 2 mechanism, that you have to check. And how you'll be able to check, basically, if they satisfies the class of linkage equation, then it will be class 1. If not, then it will be class 2 mechanism. Okay, after that we'll see what happens. Now let's consider the first case. Okay, so this one, first one. So now from here, these units are not given, so you can consider any unit. So which one is the from this length whatever is given alongside this particular link. So here this is the fixed link, okay, and it has got a length of 5 units. Okay, so here the length of the, we are writing the length of the shortest link is 5 units. That is S. We are denoting it S for small. Then from here itself we know this is the largest. That is the, this is the L. Okay, largest or longest link, that is L, equal to 9 units. And which are the other two links? This one and this one are the other two links. So you can consider anyone as P, anyone as the Q. Okay. So we are considering length of the other two links P and Q. They are 7 units and 6 units respectively. Okay. Now we know what we know. We know the class of equation is L plus S in case of a planar forward mechanism would be less than equal to P plus Q, where L and S, P and Q, these are nothing but the length of the largest link, the shortest link, and the other two links respectively. So now we have got the value for L, P, Q, and L and S. So we are just going to put it. So we'll check whether L plus S, what happens. So L plus S equal to 9 plus 5, which is 14. And P plus Q, other two link, addition of the length of other two link, it comes out to be 13. So here what happens, L plus S is, that means it is not less than or equal to P plus Q, but it's greater. So if it is greater than that, that is, it is not satisfying the Grasshopper equation. That means it doesn't belong to class 1 mechanism. Automatically it means it will be a kind of double rocker mechanism. Okay. So this is the class, you can say ultimately class 2 or doesn't belong to class 1 mechanism, and because of that it's a rocker mechanism. Okay, so the about the inversion of class 1 mechanism already we have discussed. Okay, understood how we have to check this thing? Easy only, very easy. Let me know whether you have understood or not.
Yes.
Okay,
Yes,
thank you. So, okay, so we can go to maybe anyone else. Okay, maybe second one. Other two you will just try by yourself. So second one, can who can tell me which one, what will be the L, S, P, and Q from this case?
yes, four,
So
sir.
L equal to S is 4. Okay, 4 unit. Don't forget to write the unit. Right now unit is not mentioned, so you use the word unit itself. Or if you want maybe millimeter, centimeter, as per your convenient case, you can take it, no problem. But it's basically if you write unit, okay, 4 units, then it's good. Then S is done. L
9,
9 unit. Okay. Then P and Q
7 and
okay 7 right. So 9 plus 4, that is L plus S equal to how much? L plus S 9 plus
13.
4 13 right. And 7 plus 7 P plus Q, it's 7 plus 7 14. So Is it satisfying Grashof equation? That is this one. L plus is equal to, it is less than equal to P plus Q, or it is not satisfying this. What is happening? It is satisfying, right? Yes or no? L plus S right now is, it is 13 is less than 14. So L plus S equal to less than P plus Q. So it belongs to class 1 mechanism. It is following the Grashof equation. Okay. So it belongs to class 1 mechanism. Now that is class is okay. Now what will be the type? So for that already yesterday we have discussed about the Grashof linkage. So right now here in this case, this shortest link, if you see, the shortest link is fixed. And now from a class 1 mechanism, the shortest link is fixed. Then basically what happens? It is going to form a double crank mechanism. Okay, so this is how you have to solve this problem. So other two things, I believe, other two problem, all of you can very easily find out, right? Yes.
Yes.
Let me know is there any confusion in this finding out what is class and type of the mechanism. So this kind of problem we'll be able to do, right? I believe. Okay, so this is the thing we have already discussed. That is about the class of law and class of linkage and what is class 1, class 2 mechanism. So other things you can discuss. So today, if you go through, I have already shared this particular uh, this slides as well as some initial notes that just check whether bullets are there or not. Sorry, sorry for the inconvenience. So these things already have discussed. Okay, now today we'll see how to find out the mobility of mechanism. So from the word mobility you understand that means some movement we are talking about. Okay, how it's going to behave like that, and about the degree of freedom. Okay, mobility and degree of freedom. So mobility and degree of freedom for a particular mechanism. Okay, so that is what we are going to now discuss. Now see, this all those mechanism whatever we use, okay, it is intended to do certain tasks. Yes, so and those tasks basically transmission of motion and force. Okay, that is also is important, and by using those mechanisms we want to do something, and for that a constant kind of movement of the output link, that is very much desired. And we should know that means what should be the input, how much input should be given, and what kind of output we can expect. And for that the knowledge of the mobility of the mechanism and ultimately the knowing the degree of freedom of that particular mechanism is important. Okay, so now expressing there is a term known as the number synthesis, and expressing the number of degree of freedom of a particular linkage in terms of its number of links and number of pairs of connections of different types. This particular phenomenon is known as the number synthesis. Now whenever we are going to discuss about any kind of can say mechanism that will be useful for us. Okay, so in that particular case we know that basically this linkage, okay, linkage or this mechanism, they are basically formed by the particular join of different pairs. Okay, different kinematic pairs, etc. Okay, and they will be having certain constant relative motion between them. Okay, and that we are going to utilize for doing certain tasks. Yes, up to this part, all of you agree with me? I hope yes. Okay. So now the thing is, these links. Okay, if you have suppose any kinematic link, and if these different links are not joined together, and they are not having certain relative motion, which is useful, then actually they cannot actually do the work. So some restriction are being given. Restrictions are sometimes imposed because of the, you can say, the linkage which are there. Okay, which are the connection, etc. which are there. So if you think of any unconstrained body in space, Then it has got how many degree of freedom? That is kind of independent movement which is required, or ultimately from your previous knowledge, just the independent coordinates that was required to fully describe it. And right now we are talking in terms of the motion of the. So these are the different independent motions that we are talking about. So if you think of certain anybody, any rigid body which is there in the space, so it has got 6 degree of freedom. So basically in three orthogonal axes, that is x, y, and z axis, it can have translation motion and it can also have rotational motion. So 3 plus 3 is the 6 degree of freedom that is possible for anybody which is not constant. There is no limitation to it. That means everywhere it can move, so it will have 6 degree of freedom. But whenever we are thinking of a kind of mechanism, then actually only a rigid link will not do any work. Okay, it will be definitely there will be certain connection of link with another link. So it is going to give certain like constraint on the relative motion to it, and some motion will be somewhat restricted. So now in this way, if we think of a kind of linkage, so that number of restraints it can never be zero. Number of restraints will never be zero means there have to be certain restraints, and just so 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 now, as you know, that means there will be always connection, okay? And because the number of restraints it can never be zero. That means if the number of restraints is zero, what does it mean? It will automatically mean that the joint is disconnected. That means there is no connection. So every there is no restraint, there is no connection. That will be like that. So it is of no use. So in a linkage, it can never be zero. The number of restraints can never. Similarly, it can also never be 6 also, because 6 is the final or total possible degree of freedom. Okay. Now, if all the movements are restricted, all the 6 directional movements are restricted, then actually it is of no use, right? So it can never be 0 also, and it can never be 6 also. Okay, understood? That logic all of you have understood, right? So because of that, actually, we have got yeah, we have one equation, okay, for finding out the degree of freedom for a mechanism in space. So we are talking right now about space mechanism, not federal mechanism, but later on we'll come here, this generalized equation we simplify for space mechanism also. Okay, so in the case, what basically happens, how we can will be able to find out the degree of freedom of a particular mechanism space. So now let's consider we have got like okay, let's consider we have got n number of links here. Okay, so if there are n number of links which is there, then if you consider what is the highest possible maximum possible movement or degree of freedom if you have got n links here. So total number of degree of freedom, okay, it is kind of what, theoretically speaking, if we only consider a rigid body in stress, it should be like 6 into n. But now if it has to be a kind of mechanism, we know that at least one of the link, suppose if we consider any forward decade or whatever, okay, so we know that if it has to be kind of mechanism, one of the link is fixed. That means automatically, if suppose it is like four movable links are previously there, so automatically if one is fixed, automatically means it is like 4 minus 1, 3 numbers of movable is possible. So if it is a kind of generalized way, we are thinking of like n was there, so it will be, and 6 is the maximum possible for a rigid body in space, so it will should have been 6 into 1, but because one of the link is fixed, so it will be 6 into n minus 1. Next, let's consider we have got different pairs having like if p suffix 1, it is kind of number of pairs having 1 degree of freedom, or p suffix 2, number of pairs having 2 degree of freedom, and like that. Okay, this should be 2, this word should be 2, okay, not 1, okay, second one should be 2. So they are also going to impose certain restriction. Okay, so for that we have to eliminate them also. So it will be something like, if it is number of pairs having 1 degree of freedom, so other how many degree of freedoms are restricted? 1 degree of freedom it has got. That means other 5 are restricted, because total we can have, if it was not restricted, we would have 6 degree of freedom. Now if it is kind of if it is kind of so if it is kind of P2, it's a number of pairs having 2 degree of freedom, then other 4 movements or 2 movements are possible, other 4 movements are restricted. Okay, so minus 4p2 and so on. Okay, so this gives you, this is the equation for finding out the degree of freedom of a mechanism in space. But most of the time we'll be dealing with degree of we'll be dealing mostly with immutable planar mechanism. So now most of the mechanisms are in 2D, like generally the forward mechanism or the slider time mechanism, they are essentially 2D. Okay, even though like they're kind of planar mechanism also, and here the displacement is possible along 2 axes and rotation about only 1 axis. That is total how many restraints we are allowing. Two 2 axis it is possible, that means one 2 plus 1, and rotation about only 1 axis. Okay, so 2 plus 1, 3 restraints are there, so we are living with 3 numbers of actually possible final movement. Okay, so once again the same thing, just like in the previous case it was 6 whole into m minus 1, like that we have given. So it will now start from 3 whole into, because maximum possible is 3 for one link, and it has to be at least one link is kind of fixed. Okay, so it is 3 whole into m minus 1 minus 2p1 minus 1p2. So this equation you must remember, and it will be useful for finding out the degree of freedom. So this criteria is sometimes known as Grubler'S criteria, and in some books you will also find this to be written as Kutzbach equation or Kutzbach criteria. So here this n represents the total number of links that is there in the mechanism. Okay, and we are going to find out this degree of freedom f. Okay, DOF means degree of freedom. So P1 and P2 are the number of pairs having 1 degree of freedom and 2 degree of freedom respectively. And in general, if you directly know about the number of, or generally in these cases, so P1 and P2, P1 will represent the number of lower pairs, that's easy, and it is P2 about number of higher pairs. Okay, so next we'll be interested in finding out, it is very important, degree of freedom of the mechanism. So mostly it will be planar mechanism. When it will be planar mechanism, which equation we are going to use? So 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 this particular equation we have to this equation we are going to use. Okay, so for this equation to use, by using this equation, if you need to find out the degree of freedom, what is required, you should be able to first find out properly the total number of links that is there in the mechanism. That means by this time, whatever 1, 2, 3, 4, that kind of link numbering we have done now, that is going to be very useful. You should be able to identify them. Then that is required. Then you should also be able to find out the lower pairs and higher pairs that is there in that particular mechanism. Okay, and for that the use of the importance of what is lower pair, what is higher pair, you must know. That means lower pair basically has got surface contact or point contact, line or point contact. Who can tell me? That's basically surface contact. Okay, and higher pair, line or point contact. Okay, so we'll just see whether it's a kind of it is having higher pair or lower pairs. If lower pair, then using the type of join, etc. Also, okay, how to do it, we'll be able to find it out. Okay, so today we are going to solve some initial problems, and after that we'll be discussing about different inversion of the kinematic change, like the forward mechanism. Then we'll be discussing about the inversion of your uh, slider current mechanism, etc. But prior to that, we'll just find out we'll see how to find out the degree of freedom. Okay, so we are going to use what? This equation: f equal to 3 whole into n minus 1 minus 2 p1 minus 1 p2. And sometimes if some redundant degree of freedoms are also there in that mechanism, as we have shown in one of the classes, that means when we get redundancy, okay, so that is not giving rise to any kind of like motion, okay, or that is not affecting the motion, then we call that particular degree of freedom to be kind of redundant degree of freedom. So then also if redundancy is there, that also we just eliminate. Okay, so this is the final equation you can consider that we are going to use. After this was any confusion, any problem? So now let's consider, if nothing, if we don't have any confusion. Okay, let's consider, suppose we have been given this problem. Okay, and you need to find out the different, identify the different links and pairs, etc., and find out the degree of freedom of the mechanism. So from here, these are all, you can see these are all binary joins, and there is no ternary, all not binary joins only, all okay, binary links I am talking about. Okay, all binary links, and you can see what kind of join they have got, binary, ternary, or what. So these are all hill joins, so it's a kind of lower pair mechanism. Okay, and we can start keep numbering the. It's easy one only. Okay, we can keep on numbering the. You can say links. Okay, let's consider this link is link 1, this link well and very link 2, okay, this is link 3, this link 4, this link 5, and this link 6. Okay, so this hash marking is actually eliminated, so hash marking should have been there. Okay, or I think here I have this particular figure, actually I have darken, I had darkened it, but it was, I think, in the figure it is not, it was visible. So you can see it like as if there was on headstone. So this whole thing is one. Okay, so this becomes one single link. Okay, so sorry, so not all are binary links. So actually because of the hex marking, okay, hex mark was not as visible. That's why I got confused. Okay, so this is ternary link. Okay, the whole link is on link. So next, and binary link. These are binary link. This is binary link. 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 So ABF is the ternary link, and others are kind of binary link. So total number of links we have already number n equals 6. Now you can see what kind of joints are there. So here this joint is one link and link number 6 they are joined. So two links are joined. So this is a kind of binary join. Similarly here also in this join it is only one link number 1 and link number 2 are joined. So this is binary join. Okay, here also it is binary join. Here this is three links are joined, 3, 4, and 5. This is ternary joint. Okay, so here two links are joined, this is binary join. Once again here two links are joined, binary join. Okay, so we have got 1, 2, 3, 4, 5 binary joints and one ternary join. So for 5 binary joints it is going to give you how many pairs? Directly 5 numbers of equivalent pairs, and this ternary join, one ternary joint is equivalent to 2 binary joints, and ultimately 2 number of pairs. Okay, so that is the 5 plus 2, it's 7. Okay, so our other example, so if these are easy situation, you can directly keep on count. You can keep on counting also. That means direct counting. You can do like 1 and 6. They are making one pair. Like 1 and 4. They are making another pair. Okay, like this. Okay, so that also you can do. So here there is no higher pair because we have got only pin or hinge joint. So it's kind of surface contact. That is lower pair. So there is no higher pair. Okay. So now we have got P1 should be kind of P1 only, and there is no P2. Okay, P2 equal to 0, no higher pair, and redundancy also is not there, so redundant degree of freedom also is equal to 0. So we are just putting on this equation f equal to 3 whole into n minus 1 minus 2 P1 minus P2. P2 itself is kind of 0, that's why I have not shown here. If you put it, then find out the degree of freedom of this mechanism to be 1. Okay, so this is how in this simple case we can have other cases. Okay, so that's the first one. So we can go for some other configuration. Just let me know the first one, the main thing you have understood or not. Then we can go for different situations. Just let me know.
Yes, sir.
Okay. So now let's consider this particular situation. Okay. Suppose you have this example is given for this kind of linkage. You have to find out the different links pairs, and ultimately you have to find out the degree of freedom. So these are all planar mechanism we are talking about. So directly that Grubler's equation, that is 3 whole into n minus 1 minus 2 p1 minus 2 p2. Okay. That you will be able to utilize. Okay. That just equation you just have to remember, and that is easy to remember. 3 whole into n minus 1 minus 2 p2 1 minus p2. Okay, so where we have to find out the number of links and number of lower pair and the higher pair. Okay, so first what you have to do, the identify the number of various links. I am just showing the steps. So and here you must remember that fixed or round links we generally number with the same link number. We don't give different links because ultimately with respect to the fixed link, the relative motion of the other links, if you consider, it will be same only, whether the fixed link lies here, the fixed position lies somewhere else. Okay, ultimately relative movement of a point with respect to fixed position is always same. Okay, next we have to find out identify the different number of various types of joints. Okay, and find out the number of higher and lower pairs. Also check if there is kind of redundancy or redundant pair, and use the Grubler's criteria or Kurzweil equation to find out the degree of freedom. Okay, so immediately once you get this kind of question, you have to draw that particular figure. Okay, you have to draw the particular figure, and in the figure you should number the link number. So we are drawing that particular figure. Let's consider I have drawn this particular figure, and now we need to number or identify the links. Okay, now this triangle kind of shape with hatch marking, what kind of links are they? Binary, ternary, quaternary. So this is a single link. It's not like three other different links, but the whole thing, the hatchback portion is a single link. So we have to number only like one or two or whatever it is. Okay, that particular single number. Okay, it's a single link. So let's consider we are starting from here. Okay, this is link number one. I'm giving link number two to this. Okay, this is the third link, link three, and we have got link four here. So these are the ternary link actually. Then I'll keep on numbering the other links, like suppose link 5, this is also done. This way if I go link 6, this side this is link 7, then this link is remaining link 8. Okay, is there any other link which is not numbered? So yes, all the links are numbered. So binary links n suffix b, it is 4. Ternary links n suffix t, here also it is 4. So total number of links and equal to 8. Okay, 8 numbers of links are there, we have identified here. So you need to show the links, okay, with the proper link number. Now there are actually different ways you'll be able to find out the degree of freedom, but finding out the pairs properly, if you go through the method of joins, it becomes easier. Okay, there are like you should check what kind of joins are there. Okay, and we'll be using the, you can say, the known relationship, that means binary joins equivalent to one binary joins equivalent to one binary pair. Okay, and higher joins, okay, that's ternary, quaternary. Okay, so then ternary is equivalent to two number of pairs, then quaternary equivalent to 4 minus 1, that is 3 numbers of equivalent pairs, like that. Okay, so that's why we'll just check the joins and what type of joins are there. Okay, so if it is binary, we'll keep on, we can denote with b. Okay, and for denoting binary 1 2 3 4 5 6, so b suffix 1 b suffix 2, that way we can. Similar is the case with ternary join. So here in this case, for this particular case, if you look at, it's what kind of joint is this, binary, ternary, or what? How many links are joined here in this particular connection? You can tell me how many links are joined here. So here link number 7 and link number 1, they are joined. It's not like this one is one link, this is another link, but this is the whole link is link 1. Okay, so this is the binary link. So we are denoting with b, and for ease of understanding later on, we don't, so that we don't have to keep on calculating while marking itself, we'll go like b1. Then similar is the case here. This is also link number 1 and link number 2 are joined, another binary link. We are giving P2. Here in this particular join, we have link number 2 and link number 5. They are joined here. So another binary join because only two links are joined. So third binary join B3. If I go for suppose this join, so here link 2 and link 3 are joined. So B4, fourth binary link. If you consider this join, this link 3 and this link 8 are joined. Once again, just binary join only. Fifth binary join. If you consider this join, once again join, it's 8 and 4 are joined, only two links, and 6 it is the binary join number 6. If you consider this join, here also link number 1 and link number 4 are joined. Okay, so it is the seventh number binary join, and these two links are joins are remaining, this and this. So if you look here, for this case, link number 7, link number 4, and link number 6, they are joined here. Okay, so three links are joined here, so it becomes a ternary join, first ternary join. Similar is the case in this particular joint. So link number 6, link number 5, and this link number 3, they are joined here. So second ternary join. Okay, so finding out the different joints, it is easy, right? Only you just have to check how many links are joined there, and whether it's binary ternary, just number it. So we have got binary joins. Okay, JB or B, whatever you nomenclature you use. So 7 number of binary joins, and how many ternary joins? We have ternary joins, 2 ternary joins. Now we know that binary joins directly is equivalent to one lower pair. Okay, so and this ternary joins, okay, they are one ternary pair is equivalent to two binary pair. Okay, so now basically we are interested in from this particular equation 3 whole into n minus 1 minus 2 p1 minus p2. So basically n is done. Okay, total number of links. So p1 and p2 it is required. That is number of lower pair. Okay, that is p1, and p2 that is number of higher pair. So here in this particular case, if you look at, so all are kind of binary joins, like the hinge join itself. So these are lower pairs only it is available. P2 that is higher pair not available. It is 0. And how to find out the P1? For finding out of the P1, we are actually going for the this by the method of joins. Okay. So now 7 number of binary joins. So that is 7 pair it will constitute plus two numbers of ternary join. Okay, so 2 into 2, one ternary joint is equivalent to two numbers of can say one ternary pair is equivalent to ternary joint is equivalent to two numbers of binary joint. Okay, and there are two of that kind of sort. Okay, so 7 plus 4 equal to p1 equal to 11 and p2 equal to 0. Okay, now p1 p2 everything is done, so there is no redundant degree of freedom. So now what I can do, f also is there is no f redundant degree of freedom. So we are just going to use this particular equation, degree of freedom equal to f equal to 3 whole into n minus 1 minus 2 p1 minus p2 minus fr, and we are going to just put the values 3 whole into total number of links equal to 8, 8 into 3 whole into 8 minus 1 minus 2 into p1, p1 is 7 plus 4. So here I am showing for two ternary joints is 2 plus 2, or otherwise ultimately. Okay, so minus 2 to 11 minus 0. So it's coming to be, answer is coming to be minus 1. So now can degree of freedom be negative? Actually, in the case of your normal mechanism, it will never be negative. But if it is negative degree of freedom, so it actually means that actually that's a this particular structure is not a kind of mechanism, but it's a superstructure. Okay, where we are providing some extra degree of freedom to be sure of it, so that it doesn't fail easily. Okay, sometimes that is. So this is superstructure. Similar is the case framework structure. If it is framework structure, degree of freedom equal to how much? 0. Okay, and for other mechanism, we will have some positive degree of freedom. And in general, the mechanisms are made in such a way that most of the practical mechanism you will see degree of freedom to be equal to 1. But it can be sometimes 2 or 3 also, that is different. Okay, it can have different degree of freedom, but most of the cases you'll find degree of freedom is one. Okay, so you have understood how to solve this kind of problem. You should be able to find out properly the type of links. Okay, you should be able to number those links, then the different pairs, etc. Similar is the case here if this kind of situation is there. So here we have got two fixed position. So all the fixed position will number with the same number. Okay, that's why we are showing like while numbering. This also is number one. This also is number one. Rest is similar to whatever we have just discussed. Okay, so this is similar kind of case. Just try it. Have to discuss any confusion, any question that you want to ask.
No.
Okay,
No,
so you
sir.
have understood, right? Okay, have understood the things.
Yes.
Yes,
Okay,
sir.
then okay, I'll some you just go through this kind of problems. Okay, some other try to find out degree of freedom for some other cases. I'll just discuss this. Okay, other these notes also I'll be providing. I just go through like here why I'm going to discuss. Basically, you see there is like some other element. This is cap and follower that is there, right? So other things like these are fixed position. Those things you will find able to understand. So this will be giving number one fixed position. Then this arm is this kind of thing is under link tree. This roller is has to be number three, third another one. Okay, and this is the cam portion another link four. But the interesting thing here is we have got this particular cabin follow this joint. It is forming higher pair or lower pair. Who can tell what kind of joint? Surface contact or point or line? Here we have got in this cam and this particular roller. Okay, we have got
Line.
correct line contact. Okay, so that means it's a higher pair also we have got. Correct. So number of links 1, 2, 3, and 4. Number of links. Don't get confused. That means sir, this is also another link 5. So no, it is a fixed position. This also is fixed. So it is has to be numbered with the same link number because whatever is the motion of any element you consider with respect to this fixed position, it will the same motion with respect to this position. Okay, so they are not. That's why generally we all the fixed position is numbered. Okay, fixed links are numbered. So next, because of these hinges, one and two, it is forming one link, one pair. Sorry, and two and three another. Okay, and we have one and four. And because of these hinges, okay, three binary joints we have got. Okay, three binary joints, so 3 p1 equal to 3. Similar is the case here. We are getting one higher pair p2. So here higher pair also exists p2 equal to 1. There is no redundant degree of freedom. After that, effective degree of freedom, that is already the equation already is known, 3 whole into n minus 1 minus 2 p1 minus p2. So I am just putting the values, 3 whole into 4 minus 1, 2 whole into p1 is equal to 3 minus p2 also we have higher pair equal to 1 and answer is 2. Okay. Similar is the case. All of you try this one. So, but here, what is the difference here? This is what this portion. This portion is the main thing. From the figure, who can tell me what is this? Do you recall slider crank mechanism? There also you have seen this kind of feature. So this basically is a, you can say this is a slider involved. Okay. So when the slider is involved and different links are also there. There we have got this particular pin join also for this link, that link, and 1 and 4. That is with respect to the surface itself. The slider also is making pair. Okay, so sometimes you people make mistake here. I have seen in the previous group. Suppose they will number here. Okay, they will be giving property number here. Okay, but this sometimes they make mistake. Yeah. Okay, so just go through it properly, and other some other problems maybe we'll discuss in the next class. So with this, we'll stop here for today. If you have any confusion, any question, you can ask. So how to number the links? It is okay, right? Will be able to number the links properly, identify the links properly. Yes or no? That confidence you have or not? That means you will be able to identify the links properly and numbers.
Yes.
Okay. So after that, the pairs. What about the pairs? I think the different joints you will be able to find out what type of joints you have. Yes. So from the joints, you'll also be able to find out the pairs. Okay. And you just have to check whether lower pair, higher pair both exist or not. Higher pair exist or not. And accordingly, just use the particular formula and okay. So if this will stop here for today. We'll take the attendance. Nilufal, absent. Shankar,
Present, sir.
Ashishman,
Present, sir.
Rehan,
Present, sir.
Artha,
Present, sir.
Rishikesh Basamatari,
Present, sir.
Karimiki, Karimiki, absent. Nahasal, Nahasal, absent. Keza,
Present, sir.
Rishikesh,
Yes, sir.
and Emil.
Yes, sir.
Okay, so thank you everyone for joining. We'll meet in the next class.
Thank you, sir.
Thank you,
Thank you,
sir.
sir.
Thank you, sir.
Thank you, sir.